we have our first question on the screen, which is consider the charges Q, Q, and minus Q placed at the vertices of an equilateral triangle of each side L. What is the force on each charge? Okay, we have given an equilateral triangle like this, and the charges Q, Q, and minus Q are placed at the vertices of the equilateral triangle, and the side of the equilateral triangle is L. Let's take this as L, this as L, and this also as L. Okay, let us take this vertex as A, this vertex as B, and this vertex as C. Okay, we need to calculate the net force on each charge at this point, at this point, and at this point. Okay, so how do we calculate? Let's discuss. Watch out, the charge at A. This charge Q will experience a kind of repulsive force due to this charge, and this charge will experience a kind of force of attraction due to this charge. Now let's talk about this. This charge will experience a kind of force of repulsion due to this charge, and it will experience a kind of force of attraction due to this negative charge. Okay, now let's talk about this. It will experience a kind of attraction force due to the charge at A, and it will experience a kind of force of attraction due to the charge at B. So these are the forces which will be acting at these points or the vertices. Now, what will be the magnitudes of these forces? Let's discuss. Okay, watch here. Here is the charge Q, and the charge minus Q. But the magnitude of each and every charge is equal. Since we have already defined the directions we have already defined, it means we don't need to care about for the sign of the charge. Now we don't need to care about the sign of the charge. So if it is negative, we don't care about that because we have already defined the direction of the charge. So what will be the force in each case? That will be given as F is equal to 1 upon 4 pi epsilon naught Q into Q upon the distance. The distance is L between each pair of charge, L square. And we can write it like F is equal to 1 upon 4 pi epsilon naught Q square upon L square. Let's take this as equation 1. Now, watch here. At the point A, here are two forces. Each of them will be having the magnitude F. This as F. In the same way here, this will be F. This also will be F. In the same way, this as F, and this also as F. Now we need to calculate the net force at A, at B, and at C. How to calculate the net force on each vertex we will discuss. Okay, let's talk about this point A. Okay, let's draw this point A over here. This is the point A. Two forces are acting, one in this direction, another in this direction. This is F, and this is also F. Okay, and there is an angle between them. Okay, what will be the angle between them? This is the angle between them. Since this angle is 60, why it is 60? Because it's an equilateral triangle, so this will be 120 degree. Now this angle is 120 degree. Okay, when two equal forces are acting at a point, then the resultant of these two forces will bisect this angle. The resultant will bisect this angle. So this will be 60 and this also will be 60 degree. So now how we will calculate the value of this force? We will resolve or take the component of this force in this direction and of this force in this direction. The component of this force in this direction will be F cos 60. The component of this force in this direction will be F cos 60. And the sum of these two will be given as FA, the force at A. This F cos 60 and this F cos 60 becomes 2 times F cos 60. Now put the value of cos 60, which is 1 upon 2. This 2 is cancelled by that 2 and we have the value of FA is equal to F, which is nothing but 1 upon 4 pi epsilon naught into q square upon L square. This is from the equation 1. So the force at A will be equal to 1 upon 4 pi epsilon naught q square upon L square. This is the value of force at A. Now let's talk about the force at B. Watch here. Here this angle would again be 120 degree and the same kind of system of forces is generated here. F and F with an angle 120 between them. So the force at B would be as same as that in the case of the point A. So here also the force will be the same. So we can write it like this also would be equal to the force at B. You can also calculate it like this, or we can write it like similarly. This will be equal to FB. Now let's talk about the force at C. Watch this. The force at C. At the point C, two forces are acting, one in this direction and one in this direction. The angle between them, this angle between them is 60 because this is the angle of equilateral triangle, the internal angle of the equilateral triangle, which is 60 degree. So to calculate the net force at the point C, let's draw this. This is the point C. Two forces are acting like this. This is F and this is also F. Again, two forces of equal magnitude are acting at a point, at an angle. Then their resultant will bisect this angle. So this would be 30 degree and this also would be 30 degree. So now we will take the resolution of this vector in this direction and also the resolution of this vector in this direction. So let's take the resolution of this vector in this direction. It would be F cos 30. F cos 30. And also the resolution of this vector into this direction will be F cos 30. Let's sum up them. Then we will get the value of F at C. So this F cos 30 and this F cos 30 sums up to give 2 times F cos 30. 2 times F cos 30. So 2 times F into cos 30. The value of cos 30 is under root 3 upon 2. This 2 is cancelled out by that 2, and we have the value f root 3, which is the value of the force at C. Now put the value of f from the equation 1, which is 1 upon 4 pi epsilon naught into q square upon L square, and this root 3 here. So this is the value of the force at the point C. So we have calculated the value of the force at the point C, which is this, and the value of force at A, which is this, and the value of force at B, which is also this. So in this way we have calculated these three values. Our next question is, two small identical electrical dipoles AB and CD, each of dipole moment P, are kept at an angle of 120 degree as shown in the figure. What is the resultant dipole moment of this combination? If the system is subjected to electric field directed along positive x direction, what will be the magnitude and direction of the torque acting on this? So here we have a diagram which is given in the question, and in this question there are two dipoles. One is AB, this having the charges positive q and negative q. Another is CD, having the charges positive q and negative q. Okay, and the angle between them is 120 degree. What we need to calculate? We need to calculate the resultant dipole moment of this combination according to the question. So how to calculate the resultant dipole moment of this combination of AB and CD? Let's draw them separately. This is AB, A and B. Here positive charge, and here at B negative charge. And this CD, C and D. C is having positive charge and D is having negative charge. Okay, we know that the electric dipole moment acts from negative to positive. So here the electric dipole moment will be from negative to positive, like this, towards positive. And in this case, in case of AB, the electric dipole moment will be towards positive or from negative to the positive in this direction. So, and watch here, the pair of charges here Q and Q, Q and minus Q, and here also Q and minus Q. So the electric dipole moment for both of them will be P, means the same as it is given in the question. Each of dipole moment P, and they are kept at an angle 120 degree. So the angle between this P and this P is 120 degree. So can we calculate the resultant of this P and this P, which are acting at an angle 120 degree? Yes, of course we can calculate. Let's draw this here. This is P and this is also P. Again, two equal vectors acting at an angle. The resultant of them will bisect that angle. So this will be 60 and this also will be 60. Now the resolution of this vector into this direction and the resolution of this vector into this direction. So the resolution of this vector in this direction will be P cos 60. The resolution of this vector into this direction will be P cos 60. Let's sum them up and we will get the resultant dipole moment. Let's say it PR, that is P resultant, is equal to P cos 60, and this P cos 60 becomes 2 times P cos 60. The value of cos 60 is 1 upon 2. So this 2 is cancelled by that 2 and we have the value of the resultant dipole moment as P. So this is our resultant dipole moment. According to the question, in the last they are asking for if the system is subjected to electric field directed along positive x direction. Okay, watch here in this diagram. The electric field is directed towards positive x direction, means this is the direction of electric field. So what will be the magnitude and direction of the torque acting on this? We need to find out the torque. Okay, how to find out the torque? Let's see. Okay, watch here. The resultant dipole moment is in this direction. This is the direction of the resultant dipole moment, which is like this. And this is the direction of electric field. Alright. So the resultant dipole moment is in the direction which is bisecting this angle 120 by 60 and 60. So what will be this angle? This total is 90, so this will be 30. So the angle between the resultant dipole moment and the electric field is 30. So apply the formula for the torque. Tau is equal to P E sine theta, and here the dipole moment will be applicable, which is resultant dipole moment, and the magnitude of this resultant dipole moment is P into E into sine the value of theta, that is this. The value of theta is 30 degree. Put the value of theta as 30. So this becomes P into E. Sine 30 becomes, the value of sine 30 is half. So the value of the torque is half P E. Alright, and watch here how to define the direction of this torque. Okay, as we know that tau is equal to PRE sine theta. From here we can define vector tau is equal to PR cross vector PR cross vector E. So the direction of the torque, how we will give the direction of the torque? Okay, the plane of P and E. P is in this direction and E is in this direction. This is electric field and this is resultant dipole moment, which are at an angle 30 degree. So P and E, the angle between P and E is 30 degree. So we will apply the right hand thumb rule for this. If the direction of the angle is this, then the thumb will indicate perpendicular to this plane of P and E. This will be the direction of the wrapping of the fingers, which is in the angle, in the direction of the angle, and this will be the direction of the thumb, which is indicating the negative Z direction. Watch here. This is an XY plane, this is direction X, and this is the direction Y. The angle between P and E is this, which is 30 degree. Okay, P and E. This is the direction of the wrapping of the fingers. So the thumb will indicate the negative Z direction. So we can say that the direction of Z is, direction of tau is negative Z. The direction of tau is negative Z direction. Okay, so we have calculated the value of this torque, we have calculated the value of the resultant dipole moment, and that was the requirement of the question. A spherical conducting shell of inner radius r1 and outer radius r2 has a charge q, capital Q. A charge small q is placed at the center of the shell. So what is the surface charge density on the inner surface, outer surface of the shell? Write the expression for the electric field at a point x is more than r2 from the center of the shell. Okay, they are talking about a spherical conducting shell. And a spherical conducting shell. So it is like this. Inner radius is r1 and the outer radius is r2, and this is the center. Okay, the spherical conducting shell of inner radius r1 and outer radius r2 has a charge q. The q charge is at its surface. A charge q, small q, is placed at the center, so small q is placed at the center, which is positive charge. So we need to find out the surface charge density on the inner surface and on the outer surface. So watch here. At the center, the charge positive q is there, so it will induce a negative q charge on the inside surface. Due to this positive charge, a negative charge will be induced on the surface, as we have learned in case of electrostatic induction. This positive charge induces a negative charge in the inner surface, a negative q charge. Okay, since the negative q charge is induced in the inner surface, hereby a positive q charge will be induced in the outer surface. This is due to electrostatic induction. So now the total charge on the outer surface becomes capital Q plus small q, and on the inner surface the charge is minus q. Now what we need to do, we have to find out the surface charge density on the inner surface. Okay, the surface charge density on the inner surface. So we say at it like surface charge density is represented as sigma, and we need to find out sigma inner means sigma 1. So this will be the charge inside, which is minus q, upon the area of the interior surface, which is 4 pi r1 square. So this is the surface charge density sigma 1 on the interior surface. The charge is minus q upon area is, the internal area is 4 pi r1 square. Now on the outer surface of the shell, the surface charge density, let's take sigma 2, is equal to the charge on the outer surface, which is q plus q, upon the surface area of the outer surface is 4 pi r2 square. So this is the surface charge density for the outer surface, and this is the surface charge density for the inner surface. Now one more part is there. Write the expression for the electric field at a point x is more than r2 from the center of the shell. From the center of the shell, we have to find out the electric field at a distance x, and it is given that x is more than r2. X is more than r2, hereby the point will be outside the outer surface. So whenever we need to find out the electric field from the center of the shell at a distance, then it acts like all the charge on the surface is on the center of the shell. It acts like all the charge on the conductor surface is at the center. It is at the surface of the shell, but it acts like this point charge is at the center of the shell. So when we need to find out the electric field at the point P, then we need to consider the charge which is at the surface, not the charge which is at the center, because this charge will be acting like as the charge at the center. Getting my point? Whenever we need to find out the electric field due to a conducting shell, the charge which will be considered will be the charge at the surface. This charge will be considered. So the electric field at the distance x from the center will be given as E is equal to 1 upon 4 pi epsilon naught charge. I have told you the charge will be taken of the surface, q plus q upon the distance, which is x square. So this will be the electric field at a distance x from the center of the shell, and the charge which will be applicable here will be the charge at the surface, the charge at the outer surface of the conductor. Getting my point? Whenever we need to find out the electric field for a conducting shell, for a conductor shell, we will take this charge, not the charge at the center. We will take this charge which will be applicable to find out the electric field at a point outside the spherical shell. So we have calculated this as 1 upon 4 pi epsilon naught q plus q, which is the charge on the surface, upon x square. Two infinitely large plane thin parallel sheets having surface charge densities sigma 1 and sigma 2, where sigma 1 is more than sigma 2, are shown in the figure. Write the magnitudes and directions of the net fields in the regions marked first, second, and third. So here you can see two thin parallel sheets this and this. These are having surface charge densities as sigma 1 this and sigma 2 this, where sigma 1 is more than sigma 2. Sigma 1 is more than sigma 2. Okay, what we need to do, we have to find out the magnitudes and directions of the net electric fields in the regions first, second and third. So how to calculate the electric field in the region first, second and third? First, second and third. Let's discuss. Okay, the electric field lines always originates from positive charge. Okay, so for this sheet, the electric field in the first region will be in this direction. Even will be in this direction. All right, and for this sheet, this is also positive. The electric field is away from the positive. So in this region, the first region, the electric field due to this sheet will also be in this direction. Means E1 and E2 are in the same direction. Okay, so if we talk about this second region here, then due to this sheet, the electric field is away from the sheet, which is E1, in this direction, and for this sheet, electric field is away from the positive charge, means E2 is in this direction. If we talk about this third region, the electric field due to this first sheet will be away from positive, it will be like this, and for this also away from the positive, means this would be this. So we have defined the directions of electric field at these regions. Now, how to calculate their values? Watch here. We know that the electric field due to the parallel sheets is sigma upon 2 epsilon naught. If this is E1, this will be sigma 1 upon 2 epsilon naught, and if this is E2, so it would be sigma 2 upon 2 epsilon naught. Okay, so at region first, the net electric field E first will be given as E1 plus E2. Watch here, E1 is in this direction and E2 is in this direction. So both the electric fields are in the same direction, so these will be added up. So put the values of them. The value of E1 is sigma 1 upon 2 epsilon naught, plus the value of E2 is sigma 2 upon 2 epsilon naught. This is the value of EI, and this is towards left. We have defined the direction of the electric field. Now watch here, in the region 2 there are electric fields E1 and E2. So how to calculate the resultant of two opposite vectors? We must subtract them. Subtract the higher one minus lower one. So at region 2, the net electric field at region 2 will be E1 minus E2. Why E1 minus E2? Watch here. E1 is in this direction, E2 is in this direction. So we will subtract them. Higher minus lower. Why this is higher? Because sigma 1 is higher than sigma 2. So put the value of sigma 1, E1, this is sigma 1 upon 2 epsilon naught minus E2, which is sigma 2 upon 2 epsilon naught. This is the electric field at the region second. And what will be the direction? The direction of the higher one. The direction of the higher one, that is E1, is towards right. So the direction of the resultant will also be towards right. Now let's calculate the electric field at the region third. At the region third, both the vectors are towards right. So both the vectors are in the same direction, so we will add them to calculate the resultant. So at region third, the resultant electric field will be E1 plus E2. Put the values sigma 1 upon 2 epsilon naught plus sigma 2 upon 2 epsilon naught. Both are towards right. Hereby, the resultant will also be towards right. So this is the electric field in the region third. And hereby we have calculated the electric field in the region third, in the region second, and in the region first. A hollow cylindrical box of length 1 meter and area of cross section 25 centimeter square is placed in a three-dimensional coordinate system as shown in the figure. The electric field in the region is given by vector E is equal to 50 xi cap, where E is in Newton per Coulomb and x is in meters. Find net flux through the cylinder and charge enclosed by the cylinder. Okay, here a diagram is given. A cylinder is placed in the electric field, and the electric field is vector E is equal to 50 x I cap. I cap means it is towards positive x-axis. So what we need to do, we need to find out the net flux through the cylinder. Through this cylinder we have to find out the net flux. Okay, so we will calculate the flux through this surface. Let us take this surface first. Through this surface, let us take this surface to surface second, and through this surface. Across these three surfaces we have to find out the electric flux. How to find out the electric flux through these surfaces? We will show up here. Okay, so now watch here. This surface area has an area vector which will be towards negative x-axis. The area according to the question is given as 25 centimeter square. So this will be 25 into 10 to the minus 4. 25 into 10 to the minus 4. Right? And this will be I cap but negative. So the area vector for this surface is negative 25 into 10 to the minus 4 I cap. And this surface area is at a distance of 1 meter from the origin, from 1 meter from the origin. Hereby we will take the value of x as 1 meter. So for surface 1, the area vector is minus 25 into 10 to the minus 4 I cap. The electric field is given according to the question, which is 50 x I cap, and the value of x for the surface 1 is 1 meter. So we can calculate the flux associated with this surface 1. How to calculate? Let's see. Phi first is equal to vector E dot vector A. Now put the value of vector E, which is 50 x I cap, 50 x I cap, and the value of vector A, which is minus 25 into 10 to the minus 4 I cap. So take this minus 25 into 10 to the minus 4 I cap. Here the value of x is 1 meter. So put that value. This will be 50 into 1 I cap dot minus 25 into 10 to the minus 4 I cap. Now when we multiply this and this, we will get 0.1250 I dot I. I dot I becomes 1, and this negative sign comes here. So we have minus 0.1250, the unit of flux, Newton meter square per coulomb. This is the flux associated with the first surface. Now we need to calculate the flux associated with the second surface. Watch here, this. The area vector for this surface will be 25 into 10 to the minus 4, but this time it is in positive x-axis, hereby I cap, but positive. Alright, so the area vector would be this, the electric field would be this, and the value of x. This surface is at a distance of 1 plus 1, 2 meter. This surface is at a distance of 1 and 1, 2 meter from the origin. So the value of x for this surface is 2 meter. So let's note the given data. For surface second, the value of electric field is 50 x I cap. The value of area vector is 25 into 10 to the minus 4 I cap, and the value of x is 2 meter. With the help of this given data from that diagram, we can calculate the flux associated with the surface 2. So apply the formula. Phi second is equal to vector E dot vector A. Put the values of vector E, which is 50 x I cap, dot the value of vector A is 25 into 10 to the minus 4 I cap. In this condition, the value of x is 2. So put the value of x as 2 and note this down as it is. Now when we multiply this and this, then we get 0.250 I dot I, and I dot I becomes 1. So we have 0.250, the unit of flux is Newton meter square per coulomb. This is the flux associated with the second surface. So we have calculated the flux associated with the surface 1 and the surface 2. The flux associated with the surface 1 is this, and the flux associated with the surface second is this. Now we need to calculate the flux associated with the surface third. Watch here. The area vector on this surface will be in this direction, and the electric field is in this direction. Here the area vector and the electric field are perpendicular. So in this condition the flux associated will be 0. So for surface third, phi third will be equal to 0. Why? Since area vector and electric field are perpendicular. Now we need to calculate the net flux associated with the surface. The net flux will be phi is equal to phi 1 plus phi 2 plus phi 3. Put the values of them. The value of phi 1 is minus 0.1250. The value of phi 2 is 0.250 plus the value of phi third is 0. When we calculate this, we will get 0.125. The unit of flux is Newton meter square per coulomb. This is the net flux associated with the surface, this cylindrical surface. The whole cylinder is associated with this amount of flux. Now, according to the question, look at the question. They are also asking for the charge enclosed by the cylinder. Okay, according to Gauss's theorem, we have phi is equal to q upon epsilon naught. From here, the value of charge will be q is equal to phi into epsilon naught. The value of phi we have already calculated, which is 0.125. 0.125 into the value of epsilon naught. We remember that 8.85 into 10 to the minus 12. When we calculate this, we will have 1.1 into 10 to the minus 12 coulomb. So this is the charge enclosed by the cylinder. So we have calculated the charge enclosed by the cylinder, and we have calculated the net flux through the cylinder. These were the requirements of the question. A point charge of plus 10 microcoulomb is at a distance of 5 cm directly above the center of the square of side 10 cm. What is the magnitude of the electric flux through the square? So here we have a square A, B, C, D, and a charge plus 10 microcoulomb is at a distance 5 cm above the center of the square of side 10 cm. So we have to find out the electric flux associated with this square. How to find out the electric flux associated with this square? Let's discuss. Okay, this 10 microcoulomb is here at a distance 5 cm, and the side of the square is 10 centimeter. We can create a cube with the help of this, like this. Okay, when we have created the cube, this 10 microcoulomb comes in the center of the cube, comes in the center of the cube, or at the intersection point of the diagonals of the cube. So when this 10 microcoulomb is at the center of the cube, then this cube will work as the Gaussian surface for this, and we can calculate the electric flux associated with this cube with the help of Gauss's theorem. So phi cube will be equal to q upon epsilon naught. The value of q is 10 microcoulomb, means 10 into 10 to the minus 6, and the value of epsilon naught is 8.85 into 10 to the minus 12. This is the flux associated with this cube, but according to the question, we have to find out the electric flux associated with this square. This square is the sixth face of this cube. So the flux associated with the complete cube is this. So the flux associated with this square will be 1 by 6 of the flux associated with the cube, because this is the 1/6 of the whole cube. So we can calculate the value of 1 by 6 of phi cube to find the value of flux associated with this square. So phi square is equal to 1 by 6 of phi cube. Now put the value of phi cube, which is this, 10 into 10 to the minus 6 upon 8.85 into 10 to the minus 12. When we calculate this, we will have the value of phi square as 1.88 into 10 to the 5. The unit of phi is Newton meter square per coulomb. This is the flux associated with the square. So what we have done, we have calculated the flux associated with this cube, then we have taken 1 by 6 of this flux associated with the cube, which will be equal to the flux associated with this square, because square is the 1/6 part of this cube, because this cube has 6 squares. That's why the flux associated with the one square will be 1 by 6 of the flux associated with the whole cube. So we have done this, and we have calculated the flux associated with the square. Charges of magnitude 2q and minus q are located at points A00 and 4A00 respectively. Find the ratio of the flux of electric field due to these charges through the concentric spheres of radii 2a and 8a centered at the origin. Okay, we have two charges here, 2q and minus q, which are located at these points. Okay, so we will coordinate these points. Let's see. This we have taken as x-axis, this is y-axis, and this is z-axis. Look at the points, these are a0 0. Suppose this is our a 0 0. Okay, the coordinate in y and z are 0 0. That's why we need to put this only in the x-axis. Okay, so this is the coordinate for 2q, and the coordinate for minus q according to the question is 4a 0 0. So this would be like here, that is 4a comma 0 0, and this is q. Now what we need to do, we have to find out the ratio of flux of electric field. Flux of electric field means electric flux due to these charges through concentric spheres of the radii 2a and 8a. The 2a must be in between them. This would be like 2a. The coordinates of this would be 2a, comma 0, comma 0. So if we are talking about the first sphere, according to the question, the first sphere has the radius 2a. So this would be likely to be this. This sphere would be like this. So this sphere is enclosing only the charge 2q. So the flux associated with the first sphere will be phi 1 is equal to q upon epsilon naught. The charge is 2q upon epsilon naught. Let's take this as equation 1. Watch here. The flux associated with this sphere, this first sphere, will be q upon epsilon naught. Q means charge. The charge which is enclosed with this surface is 2q. So we have taken this 2q upon epsilon naught. Okay, now come to the next thing, which is the next sphere, which is of radius 8a. The next sphere is of radius 8a. If we talk about the radius 8a, the 8a radius would be beyond this region. So this sphere will enclose this charge as well as this charge. This would be a very big sphere which is having the radius 8a. So this will enclose this charge as well as this charge. So for the sphere 2, the flux will be phi 2 is equal to charge enclosed upon epsilon naught, and here the charge will be q as well as 2q. This q, according to the question, is given as negative. The question says that this is negative q, which is placed at 4a 0 0. It is negative q. Now calculate the value. The net charge will be 2q plus minus q upon epsilon naught. So this will be 2q minus q becomes q upon epsilon naught. Take this as equation 2. What we need to do according to the question, we have to find out the ratio of these flux. So calculate the ratio of this flux. Let's take phi 1 upon phi 2. So put the values of phi 1 and phi 2. The value of phi 1 is 2q upon epsilon naught. The value of phi 2 is q upon epsilon naught. So this is cancelled out by that, this by that, and we have the ratio of phi 1 and phi 2 as 2:1. A charge q is placed at the open end of a cylinder of length L and radius R as shown in the figure. Find the electric flux through this cylinder. Okay, we have given a cylinder like this, which is open at this end. Here this is open and here it is closed. The radius is R and the length is L. So what we need to do, we need to find out the electric flux through this cylinder. How to find out the electric flux through this cylinder? Let's create the Gaussian surface for this and make this cylinder as complete. This length take as L. Now Now this charge comes at the center of this surface. I mean, the center of this enclosed cylindrical surface. So, according to Gauss's theorem, when the charge is at the center, the flux associated with this will be Q upon epsilon naught. Q upon epsilon naught. This is the flux associated with this whole cylinder. But we need to calculate only for this one from here to here. So this is half of this whole cylinder. So the flux which is required, this is the flux which is of complete cylinder. The flux which is required is the flux of half cylinder. So the flux associated with the half cylinder that is required by the question will be 1 upon 2 of Q upon epsilon naught. So this will be the flux associated with this cylinder that is required by this question. So whenever these kinds of questions are given, we must generate a Gaussian surface which makes this diagram as a whole. Then we can calculate the flux for the whole diagram. Then after that we can calculate the required value of the lactic flux, which is need to be solved according to the question. For the half cylinder, the flux is half of Q upon epsilon naught.